All right, let's start with something honest. Exact answers are great, but we don't always need them. In real math, science, and engineering, things get complicated fast, and computing an exact value can be expensive, messy, or sometimes not even possible in a clean algebraic way. So instead of asking, what's the perfect answer everywhere, we ask a smarter question. What's a really good answer near the point I care about? Think about GPS. When you zoom out, the road curves a lot, but zoom in close enough, and that same road looks almost straight. That's the philosophy of approximation. Zoom in locally, simplify the shape, and compute quickly. Same idea in calculus. Zoom in on a smooth curve near a point, call it P0, and it starts looking like a line. Zoom in on a smooth surface near P0, and it starts looking like a plane. And our ultimate zoom lens is the Taylor idea. On screen, you'll see the Taylor expansion. Don't try to read every symbol, just remember the story. Start with the value, add slope, then add curvature. Value tells you where you are. Slope tells you how it tilts. Curvature tells you how it bends. Imagine a function is temperature on a map. You don't need the temperature of the whole planet to decide what jacket to wear. You need a reliable local estimate near where you are. So in this module, we build the toolkit that makes local models work. Partial derivatives, the gradient, the Jacobian, the Hessian, and then linear and quadratic Taylor approximations. All right, first building block, partial derivatives. In single variable calculus, the derivative is just slope. But once a function depends on two variables, slope depends on direction. So the question becomes, which way am I moving? Instead of panicking, we do something simple. Change one variable at a time. Hold the other variable constant and differentiate like normal. On screen, you'll see the definition. Here's the meaning. To get the x partial, freeze y, nudge x, and measure how the output changes. To get the y partial, freeze x, nudge y, and measure how the output changes. A vivid analogy. Imagine a sound mixing board. Let x be the bass knob, y be the treble knob, and the output be loudness. Then the x partial asks, if I only turn the bass slightly, keeping treble unchanged, how much does loudness change? Geometrically, if your surface is height equals the function, a partial derivative is the slope of a slice. You slice the surface with a vertical plane, get a curve, then take the slope of that curve at the point. Quick example, if the function is x squared plus y squared, the x partial is 2x and the y partial is 2y. At the point 1, 1, both slopes are 2. Now a quick pause and try. Let the function be x squared plus 3y. What are the x partial and the y partial? Pause for 5 seconds. Answer, the x partial is 2x and the y partial is 3. So partial derivatives are like components, pieces of a bigger idea. Next, combine them into one powerful vector, the gradient. If partial derivatives are your x slope and y slope, the gradient is the big picture. On screen, you'll see the gradient written as a vector made from the partial derivatives. Intuition-wise, remember this phrase. The gradient is an uphill compass. Imagine you're standing on a hill and you want to climb as fast as possible. Which way should you step? The steepest uphill direction is the direction of the gradient. 3 key facts. First, the gradient points in the direction of steepest increase. Second, the size of the gradient tells you how steep that steepest direction is. Third, when the gradient is not 0, it is perpendicular to level curves. Level curves are contour lines, places where the function stays constant. If you walk along a contour line, your height doesn't change. So the direction of greatest change must be perpendicular to those curves. This connects to the directional derivative. On screen, you'll see a dot product formula. The important idea is the directional derivative is how much the gradient points in the direction you're walking. And for the clean interpretation, that direction should be a unit direction. Another vivid example, smell intensity. If the function measures how strong a smell is, then to find the source, you walk where the smell increases fastest, along the gradient. To escape, you go opposite the gradient. Now another pause and try. For the function x squared plus y squared, find the gradient at the point 1, negative 2. Pause for 5 seconds. Answer. It's the vector 2, negative 4. Before we move to vector outputs, one important 3D case, level surfaces. If you have an implicit surface like big F equals a constant, then the gradient of big F points normal to the surface. That gives the direction perpendicular to the tangent plane. Now, the gradient handles scalar outputs. What if your function outputs a vector? That's where Jacobians come in. Quick bridge. When a function outputs a vector, we can still differentiate component by component. In one variable, if you have a vector-valued curve w of t, then w prime of t points in the tangent direction of the curve. In multiple variables, we organize all those component derivatives into a matrix, the Jacobian. On screen, you'll see the Jacobian matrix. Rows correspond to outputs, columns correspond to inputs. But the most important meaning is not the grid itself, it's what the Jacobian does. The Jacobian is the best linear approximation of a vector function near a point. In plain English, if you nudge the input a tiny bit, the Jacobian predicts how the output changes. Direction and amount. Robot arm example. Inputs are joint angles. Outputs are the hand's position. The Jacobian tells you, if I nudge the joint slightly, which way does the hand move and how much? Or in graphics, mapping x, y to uv. The Jacobian tells you how a tiny neighborhood gets stretched, rotated, and sheared. And if the Jacobian is square, its determinant has a geometric meaning, local area or volume scaling, plus whether orientation flips. If the vector function is x plus y and x minus y, what is the Jacobian? Pause and try. Answer. It's a constant matrix. First row is 1, 1. Second row is 1, negative 1. Next, back to scalar functions. But now we go to second derivatives, the Hessian. Gradient tells us slope and direction, but slope alone doesn't tell you how the surface is bending. That bending, curvature, lives in second derivatives. The Hessian is the matrix of second partial derivatives. On screen, you'll see its layout. A helpful fact, the Hessian is the Jacobian of the gradient. Now for the intuition, the marble test. If the surface is bowl-shaped, a marble rolls toward the bottom. That's a local minimum. If the surface is hill-shaped, it rolls away. That's a local maximum. If the surface is saddle-shaped, it rolls down in one direction, but up in another. That's a saddle point. Eigenvalues describe curvature along special directions, principal directions, where the quadratic behavior is pure. Mini-check. X squared plus y squared is a bowl, and x times y is a saddle. Now we have the full local shape kit: value, slope, curvature. Next, build approximations. Let's do the simplest useful approximation, the tangent plane. Near a point p0, the function behaves like value at p0 plus the effect of tiny changes in x and y, weighted by the partial derivatives at that point. On screen, you'll see the linear approximation written in both coordinate form and gradient form. The message is, linear approximation matches the surface's height and tilt at the point. Mental picture, a tiny flat board pressed onto a curved surface. Right at the contact point, it fits perfectly, and nearby, it's a good approximation. Important clarification. This is the tangent plane to a graph. Z equals f of x, y. For a level surface, big F equals a constant. The tangent plane uses the gradient normal form. Why is linear approximation powerful? If the function is smooth enough, the error shrinks roughly like distance squared. Get closer, and accuracy improves fast. We'll do a clean example on screen. X squared plus y squared near the point 1, 1. Then we'll estimate a nearby value to feel how accurate it is. But linear has a weakness. It's flat. It ignores curvature. So now we upgrade. Quadratic Taylor is basically, what if we also model the bending? On screen, you'll see the quadratic approximation written using the gradient and the Hessian. You don't need to read every symbol. Just remember the structure: value plus a slope term plus a curvature correction. Two vivid pictures. Linear is a rigid board. Quadratic is a flexible patch. It can bend and it can even twist if the mixed term matters. Driving analogy. Linear assumes the road is straight. Quadratic also accounts for the turn, so it stays accurate longer. And if the function is smooth enough, quadratic becomes dramatically better near the point. Quick sanity check. If the original function is already quadratic, then quadratic Taylor matches it exactly. Now let's tie everything together with one complete example and bridge to optimization. We'll run the full pipeline on one function shown on screen. Step 1, compute the gradient. Step 2, compute the Hessian. Step 3, set the gradient equal to 0 to find the critical point. Step 4, use the Hessian test to classify it. Then we build local approximations at a simple base point like the origin, a linear approximation, and a quadratic approximation. And here's the satisfying part. If the function is quadratic, the quadratic Taylor approximation reproduces it exactly. Now, the bridge to gradient descent. You don't need perfect global control. You just need a reliable local direction and the willingness to iterate. Gradient descent does exactly that. Start somewhere, look at the gradient, take a small step downhill, meaning opposite the gradient, and repeat. On screen, you'll see the update rule. We'll do a one-step mini demo so it feels real. Closing thought. A lot of powerful math comes from one idea. Make the world locally simple, then iterate.